Hello everyone. Today we're going to be pricing some options and some more general assets and not just put call parity like last time. So in exchange, we do have to work with a more simplified framework, and the one we're going to be working with today is called the binomial model. So let me introduce that. As usual, we're going to be working with an underlying asset S, a time t that's spot price ST, and then a time big T in the future. It's going to have a payoff S big T, which is going to be a random variable. And the random variable is going to be SU with probability P between 0 and 1, and SD with probability 1 minus P. SD is in down and SU is in up, where SD is going to be smaller than SU. So it's going to go up, probability P, and down, probability 1 minus P. Now, before, in the previous video, we introduced what the payoff of options were. So the payoff of a call option, if you're the holder, is ST minus K, and if you have a put option, it's K minus ST plus, where K is the strike price and plus just means the maximum of the thing inside the brackets and 0. But now we're going to instead of valuing just options, we're going to value a more general assets. So let's introduce such an asset, and this we're going to call asset V. And this asset is going to depend on the underlying asset S. So it's going to depend on what ST is, on what S does in the future. So this asset is going to be worth VT in the present, and a time big T in the future. The payoff is going to be VU or VD. VU if ST equals SU, so if the underlying goes up, and VD if the underlying goes down. Now, how are we going to value? And by the way, VU and VD can be anything. We're working on a very general framework here. We're considering any asset we're assuming there's an asset with these characteristics, and we're going to try to price it. In the case of the options, VU would be SU minus K, U at the top, and VD would be SD minus K, for a call option and for a put option similarly. Now, how are we going to value this asset? We're going to do it in the way we always do it. We're going to build a portfolio and we're going to use the no arbitrage principle. So let's start. A time small t. We're going to start with 1 of asset V. 1 of V. And then we're going to take minus delta of S. This delta is a variable. We're not going to decide what it is yet, but we will choose it in the future so that it's convenient to work with. Now, we want the price of the portfolio, the value of the portfolio at the very beginning, to be equal to 0 in order to apply the arbitrage principle. So we're going to take away minus VT and we're going to add delta ST in cash. Right? Because then this is worth VT, which cancels out with this, and this is worth minus delta ST, which cancels out with this. Now, we're going to try to solve for VT, which is the price of this asset at the present time. Okay, so let's inspect what the payoff at time big T is. Well, V is going to be VU or VD depending on what the underlying does. The underlying is going to be minus delta SU if it goes up, minus delta SD if it goes down. Oh, by the way, this adds up to 0. And then we have the cash, which is always going to be the same amount. The cash does not depend on the underlying asset. The cash is just cash. So it's going to give us this. And we take into account the continuous compounding interest. So in the first case, this is going to be the payoff, this thing plus this, and in the second case, it's going to be this plus this. Okay, now, since this depends on what the underlying does, we want to choose delta so that ideally that's not the case. So if this were to be independent of the underlying, that is deterministic and not a stochastic process, then we would need VU minus delta SU to be the same as VD minus delta SD. So let's solve for that. VU minus delta SU equals VD minus delta SD. And this gives us delta is VU minus VD over SU minus SD. So if we choose delta to be this is deterministic. And the value of this thing here is going to be VU minus delta SU plus minus VT plus delta ST e to the R T minus T. In the first case, and this, I'm not going to write the cash down, this in the second case. But since these two are equal, the top case and the bottom case, these two amounts are the same. It's going to be deterministic. But now, so these two are the same. But now we start with 0 amounts of money. So both of these, which are the same thing, have to be equal to 0. Why? If this were positive, then we'd be making positive amount of money, starting with no money. And if this were negative, we could short sell this portfolio, so take negative amounts of everything, and we would get a negative amount of minus of a negative amount, which is a positive amount. So this whole thing has to be equal to 0. So if we just focus on the first equation, right, because this is equal to this, which is equal to 0, we get that solving for VT, we get that VT equals delta ST plus e to the minus R T minus T VU minus delta SU. And this is the formula for the price of the, with no arbitrage, of the asset V at time small t. Now, I broke this down a bit more than I should have. So usually what you just do, I'm going to write it down here, is you don't worry about the cash. You consider 1 of V and then minus delta of S. And this is worth V minus delta ST, sorry, this amount. And then at time t, this is worth VU minus delta SU, VD minus delta SD. Again, you choose delta in the same way so that these two are equal. So say this is equal to this. You choose delta this way. And now what you do is, since this is deterministic, this has to be equal. It's a risk-plus investment, so this has to have the same return as the compound interest. So VT minus delta ST times e to the R T minus T has to be equal to this thing in the right. And you arrive at the same equation here, but you don't have to deal with the cash separately, which is a bit more of a hustle. So you get the same thing. Okay, so this is the formula that we get for the option. But it's quite a messy formula. And it doesn't really tell us anything because it's very difficult to know what's going on here. So we're going to introduce something called the Arrow-Debreu securities. But before we do, I just want to claim one thing. I want to claim that ST ER T minus T is strictly between SU and SD by the principle of no arbitrage. If this weren't true, say this inequality was false, then we would have that SD is more than SU, is more than equal to ST e to the R T minus T. And the problem with having this is that what we could do at the present time is we could short sell one of the underlying assets, obtain S small t, invest this in cash in the future. At time big T, we would have this amount of money because of compound interest. We started with ST, now we have ST times this constant. And then we have to pay back the underlying asset S. We have a negative amount of that, we have to pay it back. And the thing we have to pay back will either be minus SU if it's gone up, or minus SD if it's gone down. In the first case, it's a non-negative amount, right? It might be a negative amount, but ST e to the r t minus su is going to be a non-negative amount. So the amount of money we end up with after paying the underlying asset that we owe is greater than or equal to 0. If, however, the underlying asset has gone down, then this is going to be SD, and this is going to be strictly greater than 0. So in the first case, we're guaranteed to not lose any money, and in the second case, we're guaranteed to make some positive amount of money. So by no arbitrage principle, this can't be the case. This inequality here that I just showed by contradiction has to be false. So we just proved this thing here, this inequality here, and we can prove this inequality in the same way. If we had st e to the r t minus t is more than or equal to sd is more than su, then what we do is we short sell. We buy the underlying asset S for st amounts of money at the present time, right? So we have this and one of the underlying assets, one of S. At the future time, this is going to become minus st times the constant, the time value of money, this e to the r t minus t. And this is going to become either su or sd. In the case 1, we're going to have su minus this, which is positive. And in the case 2, we're going to have sd minus this, which is non-negative. So we're guaranteed to not lose any money, and there's a chance that we might make a positive amount of money. So by no arbitrage principle, this inequality also has to be true. Okay, so we have this inequality. I did it a bit quickly because it's not very relevant until later on, but anyway. Okay, so now let's focus again on the Arrow-Debreu securities. What are these? Well, these are sort of like a basis for a vector space. We're going to assume that such securities exist. We're going to assume that there exists a security AU and a security AD, such that they depend on the underlying S, and AU is going to be 1 if the underlying goes up, and 0 if the underlying goes down. And AD is going to be the opposite. 0 if the underlying goes up, and 1 if the underlying goes down. Now, why are these useful? Well, we'll see later on. But first, let's value these securities at time small t. We can use this formula, and well, we can use this thing we just proved to find AUT and ADT, their prices at time small t with no arbitrage. How do we do this? Well, we can just apply this framework of asset V to these. We can let this be VU and this be VD. And then we just substitute the values here. So VU equals 1, VD equals 0, and plug it in here. So plug the values, these values, into this formula to get this. And we can do the same thing for AD. The problem is it's very boring stuff and it takes a lot of rearranging. So I'm just gonna show what you get, but I won't show the process. So, and again, if we let this be VU and VD, in the first case, we're gonna get that this is Q times e to the minus r t minus t, and this is 1 minus Q times e to the minus r t minus t. Where Q, we're going to define to be e to the r t minus t, st minus sd over su minus sd. So if you substitute these values into here, you get that AUT is this, where Q is this, and ADT is the corresponding amount. Now, we need to delete this just to avoid getting confused. Why are these two things useful? Well, actually, first of all, let's go back to this inequality I just showed. This inequality here implies that this is between 0 and 1. It's greater than 0 because of the first inequality, and it's smaller than 1 because of the second inequality here. Okay? Now, why is this useful? Well, as I said before, these securities are sort of a basis for other assets. We can build other assets with these by taking a linear combination. So for example, we're going to go back to an asset V. We're going to fix it, whatever asset it is, with V, U, and VD being constants. And I'm going to claim that V is the same thing as taking VU of asset AU and taking VD of AD. What do I mean by this? Well, if we build a portfolio with VU of this security, that does this if it goes up, this if it goes down, etc., and VD of this, then the payoff at the expiry date, the time big T, is going to be the same for V and for this thing here. How so? Well, if the underlying goes up, the payoff for V is going to be VU, and if it goes down, it's going to be VD. Now let's focus on the right-hand side. If it goes up, AU is going to be 1, the payoff, and AD is going to be 0. So this whole thing is going to be VU, the same as V. And if the underlying goes down, then AU is going to be 0, and AD is going to be 1. So this whole thing is going to be VD. So this portfolio on the right behaves in the exact same way as V. It has the same payoff. So what can we say from this? From this we can say that the price of VT and the price... Sorry, there was a problem with the video, it cut out. What I was saying, the payoff of V and this hand, and so the left hand side and the right hand side is the same time big T. So the price of this and the price of this has to be the exact same at the present time. Why? Suppose the left hand side VT, the price of the left hand side VT is less than the price of this. What we can do is we can short sell the right hand side, obtain some amount of money. With that amount of money, buy the asset V, and we have some left over because this is more expensive than this. And then we wait until expiry date, and the expiry date, the payoffs cancel out. So we don't need to do anything, they cancel out. And we're left with some positive amount of money times the constant, times the time value of money, but it's still a positive amount. Which means that by no arbitrage, we would start with 0 amounts of money, and we'd be getting guaranteed a positive amount of money. That can't happen. So these two things have to have the same price at times more T. So what does that mean? That means that VT has to be VU times AUT plus VD times ADT, right? The price, and these are just constants. But if we go back to the thing we just, the formulas for AU and ADT, this is going to be equal to e to the minus r t minus t. We factor that out, and then we get q VU plus 1 minus q VD. Now, why is this more significant or more shows more of what's going on behind the scenes than this thing here? Well, let's go back to the very beginning, the underlying S. We said that ST is a random variable that takes SU with probability P and SD with probability 1 minus P. Now, what's the expected value of, you can see, okay, yeah. What's the expected value of ST? Which is going to be P times SU plus 1 minus P SD. This greatly resembles this thing here. This is saying that if instead of Q we had PVU plus 1 minus P VD, this would be the expected value of the return, the payoff of VT. So if instead of using P, we use Q and denote the fact that we're using Q instead of P with this symbol, Then this is equal to e to the minus r t minus t times, let me rub this out, times the expected value using q of vt. So the price of this asset depends on the expected value of what the asset is going to be, discounted by the time value of money. Again, using Q and not P, so using a different probability measure. So this is the result that's most significant, and we're going to be, it's going to pop up many times in the future, in many videos. In the next one, which I'm going to be doing the fundamental theorem of asset pricing in a bit of a more general framework than the binomial, it's going to pop up again, and it's a much more indicative expression than this one of what's really going on behind the scenes. And let me see if I have anything else left to mention. Well, I mean, just to be a bit pedantic, the reason why we insist on this being smaller is to avoid this being, well, delta being infinity. And the reason why, so that's why I mean, instead of just being smaller than or equal to, and the reason why we need p to be between 0 and 1 is because otherwise we, when we derive this formula, we're assuming by no arbitrage that it's basically non-deterministic. So that's why we need to assume between 0 and 1, but that's not really important. And yeah, I think that's all I wanted to say. Yeah, I hope you enjoyed the video.